After our last video and the one where China put a supercomputer in orbit while America filed paperwork, one comment kept collecting likes. You can't cool computer chips in a vacuum. No hype, no emojis, just physics. Here's the uncomfortable part. That comment is correct, and SpaceX knows it, Google knows it, China knows it. Every single plan to put AI in space, American or Chinese, lives or dies on this one problem. So today, the physics, the real numbers, the 4 bets being made against thermodynamics, and why this problem might actually be America's best chance to win. Space is about minus 270 degrees Celsius. So cooling a computer up there should be the easiest thing in the world, right? Wrong. And the reason is so simple, it hurts. On Earth, your laptop survives because air carries its heat away. A data center in Virginia survives because fans blow air, pumps push water, and cooling towers dump that heat into the sky. All of that is convection. Heat leaving through stuff that touches other stuff. In orbit, there is no stuff, no air, no water, nothing touches anything. A vacuum isn't cold in any useful sense. A vacuum is the best insulation in the universe. It's literally how a thermos keeps your coffee hot for 6 hours. Now imagine running 100,000 gaming PCs inside the thermos. That's a space data center, which leaves exactly one exit for heat, radiation, glowing it away into the dark like an ember. And radiation is slow, painfully, brutally slow. Every watt of computing you run in space needs surface area. Big, flat, dumb panels whose only job is to sit there and glow. Remember that word, area. It's about to get expensive. Let's put real numbers on this wall, starting with the biggest thing humans have ever built in space, the International Space Station. American-led, American-built, 30 years of engineering pride. The station rejects its waste heat through ammonia loops, feeding 6 radiator assemblies. 8 panels each, 48 panels total, roughly 400 square meters of radiator, an area bigger than a basketball court. And all of that hardware dumps 70 kilowatts, 70. That's the power draw of a few suburban houses. It took the largest, most expensive structure ever flown to cool a cul-de-sac. Now scale that up to what the AI race actually needs. Starcloud, the American startup we'll get to in a minute, published the math in their own white paper, and credit to them for showing their work. A 1 square meter black panel at room temperature radiates about 838 watts into deep space, using both sides. Sounds fine, until you remember what a real AI data center produces. 1 gigawatt of computing means 1 gigawatt of waste heat. That's a mid-sized American city's worth of power, all of it turning into heat, all of it needing to glow away through panels. Do the back of the envelope division, and you need over 1 square kilometer of radiator. That is roughly 170 football pitches of wing mirror, flying in formation at 17,000 miles an hour, forever. So when someone says, just put the data centers in space, the rocket was never the hard part. The hard part is the glowing wall the size of a small town that has to come with it. And whoever builds that wall cheapest wins everything. So how do you beat thermodynamics? 4 players, 4 bets, 2 flags. Starcloud, the American startup, is betting on structure. And before you dismiss them, last December, Starcloud trained an AI model in orbit on an NVIDIA chip, backed by NVIDIA itself. First ever, that's an American first. While everyone was arguing on the internet, a company out of Washington State quietly ran the experiment. Their 5 gigawatt concept is a single platform with solar and cooling panels stretching about 4 kilometers across, fed by 2-phase cooling loops, liquid boiling into vapor, carrying heat to the radiators. If deployable structures that size can work, they win. But nothing 1/10 that size has ever been unfolded in space. It's the boldest bet on the board. Google is betting on staying small. Project Suncatcher isn't a gigawatt monolith. It's 81 satellites carrying Google's own efficient TPU chips, starting with just 2 prototypes in early 2027, built with Planet Labs. Less power per satellite means radiators that actually fit on a satellite. Google isn't fighting the wall. It's politely walking around it. Clever. But 81 small satellites will never carry serious compute. It's a science project with a $1 trillion company's logo on it. SpaceX is betting on brute force. They're filing asks for up to 1 million orbital data center satellites, 100 kilowatts of computing per ton launched. Translation? Launch so much radiator area so cheaply that the problem drowns in Starship cadence. It's not an engineering answer. It's a logistics answer. And honestly, it's the most American answer imaginable. Don't outthink the wall, outbuild it. And China? Here's the twist from our last video. The three-body constellation's 12 satellites are small enough that ordinary satellite thermal control handles them just fine. China didn't solve the cooling problem. China dodged it. For now. Their plan is 2,800 satellites and a full exascale computer in orbit. And physics doesn't check passports. Scale up, and Beijing slams into the exact same glowing wall as everyone else. The head start you've heard about? It expires. At the wall, notice what just happened to this race. The question stopped being who has the best rockets and became who has the best radiators. Up there, radiator area per watt is destiny, and every path is ugly. Two-phase cooling in zero gravity is genuinely hard. Bubbles don't rise when there's no up. So the elegant physics that works in your refrigerator misbehaves in orbit. Kilometer-scale panels are a debris target the size of a city district, and one pinhole strike doesn't just break a panel, it bleeds the coolant that feeds it. Small formations dodge all of that, but can't deliver the compute. Big platforms deliver the compute, but bet everything on structures nobody has ever flown. Here's the part the doomers miss though. If the race comes down to who can put square meters of glowing panel in orbit for the fewest dollars, that's not a physics contest anymore. That's a launch cost contest, and there is exactly one machine on Earth designed to crush launch costs. Starship. China started the clock, no question. But the wall at the end of the race is made of area and dollars, and America owns the only factory that prints both. The first real test flight of that idea is already in orbit, running an NVIDIA chip, wearing an American flag, metaphorically. We checked, there's no flag sticker, yet. So the comment was right. You can't cool chips in a vacuum. Not easily, not cheaply, and definitely not for free. China's 12 satellites dodged the problem. America's million satellite paperwork ignores it. And the winner won't be whoever launches first. It'll be whoever makes a square meter of glowing panel cheaper than everyone else on the planet. But there's one man who thinks all of it. The radiators, the lasers, the million satellites, both flags, fails a much simpler test. He's running a $500 billion AI project. He's one of the most powerful investors alive. And he says the math is broken at step one. Is he right? That's the next video, and it might be the most uncomfortable one in this series. This episode exists because of a comment, so leave the next one below. The best comment gets the next deep dive, and yes, we actually read them. That's how we ended up here. Subscribe, and we'll see you in orbit.